Okay, so we're going to kick this quarter off by diving right into the concept of energy. Energy is a pretty abstract and pretty difficult to define concept without defining a whole lot of other physics terms first. So a general definition to get us started is that energy is the potential of an object to create change in its surroundings. So an object that has lots and lots of energy can create really big change, and an object with very little energy will create not so much change. And the kinds of changes we're talking about could be changes in position to move an object from one place to another, energy to change temperature to heat something up, energy to change color. Whatever those changes might be, energy is the source. So when we define the energy of a system, we're defining the potential of that system to produce some sort of change in the surrounding environment. And one of the most important things about that definition is that energy can be moved around into different forms, so that in some sense, it doesn't matter what kind of energy you have. If you want to do something that takes energy, any form of energy will do. So we use a lot of energy. A low-tech society, one from before the Industrial Revolution, used about 100 joules of energy per person every second. Now, a joule might not be a familiar unit for you. We'll be learning more about it later, but one comparison would be that if you drop a 2-pound or 1 kilogram object from a height of 10 centimeters, that's about 4 inches, it hits the ground with an energy of 1 joule. So imagine dropping a book from a few inches up. The amount of energy that it hits the ground with, that's 1 joule. That's not very much. But pre-tech societies used 100 of those every second for every person. That would be in the form of food, fire, draft animals, and tool usage. Our society, on the other hand, averages a much higher usage rate, 10,000 joules per second per person, 10,000 dropped books per second per person. Think about that for a moment. And I think it's really important and interesting to think about where that energy usage is happening. Is it all in our homes? Is it our food? Is it our cars? It's so much larger than pre-tech peoples, but it allows us to focus on a lot more things than just acquiring food. When you think about the wealth of modern society compared to pre-tech societies, that wealth is not really about money. It's about energy. And where is that energy coming from? So here I'm going to show you some data from a website that collects statistical data on energy usage worldwide. I'll put the link in the slides so you can take a look at it yourself. So if you click on that, you can go straight to this webpage I'm about to show you. And there is the webpage. So here we're looking at worldwide energy usage in each country in 1990. So each country, 1990. 28 years ago. The colors on the map are showing groups of countries by energy usage. So the darker the color, darker colors like the United States and Russia and China, the more energy that country was using in 1990. And the numbers in the table are the data. You can see the United States was by far the largest, more than twice as big, as much energy usage as the second largest, which was Russia at the time. So a couple of things about these numbers. The units. We will keep running into this issue. We'll talk about it a lot. The energy is measured in different units for every resource you look at. So we will always have to pay attention to units and how to relate different units to each other. This happens because it is more convenient to measure some forms of energy in one unit than in another. The numbers in this table are millions of tons of oil equivalent. That's what the MTOE stands for. So even though every country uses a lot of different forms of energy and some don't use very much oil at all, the data in this website has been combined so we can say if everyone only used oil for every single energy need, then the amount they would have used is 1,910 million tons of it in the case of the United States, and 882 million tons of it in the case of Russia. Second point to remember, these are absolute numbers, meaning this is the amount of energy each country actually used in total. But countries don't have the same populations, nor do they have the same kinds of economies and needs all the time. So this comparison can be a little misleading. maybe there's a really small country in this list that looks like it has small energy consumption, but it wastes a lot. So its usage per person is actually really high. And also maybe there's countries with large populations that don't use as much per person. So their comparison numbers really should be lower than what the absolute numbers say. So China is really important in that respect, because you can see that even though it had 4 times the population of the United States in 1990, it used less than half as much energy in total. So that is a much lower usage rate per person in China at that time. All right, now I'm going to switch it up to the last year, and you can see that you can play, so you can look at 1 year at a time in this. So I'm going to push up to 2017, and you can see that a lot has changed. Russia has dropped down a couple of places, and its total energy usage has dropped a little bit as well. The US has increased its total energy usage a little bit, but India and China in particular have increased a lot. Compare what they were in 1990 to what they are in 2017. And China is now the largest overall user of energy at 3,105 million tons of oil. That change is probably connected to big changes in standards of living and poverty rates in those countries, and it is really impressive. Those countries have done an amazing thing in a relatively short amount of time. Also remember that China and India both have populations about 4 times larger than the United States. So their energy usage per person is still significantly lower than it is in the United States. So I'd like you to explore that webpage a little and figure out in what year China passed the US in total energy usage. You can do that by moving the slider around and look at the change over each year. But for now, we're going to go back to my slides, and there, again, there's the link to get to that website. So let's think a little bit about the history of energy usage. When humans started out, something like 200,000 years ago, almost all of our energy came from food. So we could use muscle power to do work, and almost all of that work went back into acquiring more food. A long time ago, maybe 5 to 10,000 years, we began to use other animals to aid us and to use water power to do some of our work. That made larger scale agriculture possible, which made it possible to support division of labor, larger towns and cities, and some of our labor wasn't directly tied to getting more food anymore. Then, in the late 18th century, we started building machines that used steam power derived from burning wood. So firewood and at that time, firewood and muscular effort still provided the bulk of our energy. And then in the 19th century, things began to change much more quickly as energy supplies that were more dense in energy and more easily transportable and tradable, such as coal and oil, were discovered and developed. So in the distant past, we got more energy from food than we put into acquiring it. If you think about it, if that hadn't been true, our species would not have survived. You must get more from the food than you put into it. But today, because we have so much energy available from other sources than food, we put more energy into the process of getting food than we can get from eating it. That is not true for other animals, and that is a very interesting point for our species to be at in history. But those changes mean that we're blowing through our resources at a phenomenal rate. We have to think about how long those resources can last and what other impacts use of those resources have on ourselves and the environment. So in this figure, you can see the advent of coal in the middle of the 19th century right there, and then coal increases from there. And you can see petroleum and natural gas at the beginning of the 20th century and hydroelectric power. You can also see nuclear power, and I think solar power is hidden in here down at the bottom. Notice also that this graph is using a different energy unit than we had used previously. This one is in quadrillion British thermal units. So all of these energy sources have been converted to the same scale, but not the same as the one we were using in the other graph. That allows them all to be compared together. So where does energy come from today? What does it look like today? So you can still see that petroleum is our number one source. Coal is number 2. Natural gas is number 3, close behind. And the alternative fuels such as hydro and geothermal and wind are small. But that also means that because they're small, there's a lot of potential for development in those areas. And we want to think about development in those areas because those fossil fuels, petroleum, coal, natural gas, have a limited supply. Again, notice that the scale of this table is different again. Here we're using joules, 10 to the 18th joules per year. 10 to the 18th is a billion joules per year, and this is total for the entire world. Also notice that all but 2 of these sources have these asterisks, which means that they are ultimately derived from the sun. So only geothermal and nuclear are not directly or indirectly derived from the sun. So you can think of fossil fuels, which don't seem like they're related to the sun, as being like many thousands of years of sunlight energy, which was used to grow plants originally, compressed into rocks or into oil. So when we burn petroleum or coal or natural gas, what we're doing is we're burning the energy that came ultimately from the sun many years ago, and we're doing it very quickly. All right, so let's talk about those energy units for a moment. The different resources traditionally are measured in different units because it makes more sense to measure coal in tons because it's a rock and you have to use a lot of it to run a power plant. And oil is convenient to measure in barrels because it is a liquid that was traditionally transported in barrels. So people measured how much energy they would get from burning the entire barrel of oil. And natural gas is a gas, so it makes sense to measure it as a volume. Cubic feet is one measure of volume, and for large amounts, for like an entire country, it makes sense to scale that to trillions of cubic feet. Our book mostly uses the British thermal unit as its unit to compare everything in. That's a unit that was traditionally used for measuring heating fuel for use in homes and factories. So you can see in the table that 1 ton of coal has the same energy as 25 million British thermal units. 1 barrel of oil has the same energy as 5.8 million British thermal units. So 1 ton of oil is about 1/5 of, 1 barrel of oil is about 1/5 of the energy of a ton of coal. And then 1,000 cubic feet of natural gas is about 1 million BTU. And then when we think about the consequences of using this energy, we might want to think about something like the BP oil spill. The BP oil spill happened in 2010 in the Gulf of Mexico, and there was an explosion in the drilling rig that caused millions of gallons of crude oil to be spilled into the Gulf of Mexico. On average, it was about 210,000 gallons of crude oil spilled into the Gulf each day, and for a total of 11 weeks. Now that was energy that could have been used to power cars or to power homes, to power industry. What does that number really mean, 210,000 gallons? I'm going to post another video working through the unit conversion to see how much energy was lost in all of those gallons of oil spilled and what that energy could have been used for. That will help us to practice the unit conversions and to think about the scales of energy usage. So that's the question we're going to be answering. How much energy was lost in that spill, given that it was 210,000 gallons of crude oil per day for 11 weeks, and each barrel holds 42 gallons. All right,